Today, our group is excited to introduce our project, which centers on a major global challenge: restoring and improving urban infrastructure. Around the world, engineers work to create safer, stronger, and more resilient cities. And one of the most important aspects of that work is designing buildings that can withstand natural disasters. To explore this idea, our exhibit features an earthquake shake plate, a hands-on demonstration that lets visitors actually see how different structures hold up under simulated earthquake conditions. The problem our team wanted to address was how to help young students understand the importance of resilient building design in a way that feels intuitive, engaging, and fun. Our objective is to show students ages 5 through 18 how engineers can approach real-world challenges, especially the challenge of creating structures that can survive seismic activity. We also want to highlight how multiple fields, civil, mechanical, and electrical technology, work together to solve these large-scale problems that shape the world around us. The design problem we focused on was how to create an exhibit that's educational, interactive, and accessible for a wide range of visitors. Primary audience is K through 12 students, many of whom are already curious about STEM topics, and while the exhibit is open to everybody, we expect that young learners with interests in engineering, innovation, or hands-on learning will be especially drawn to it. Overall, our target customers are the students attending the exhibit fair who want to explore how engineers solve modern infrastructure challenges.
To meet our goals, we created both general and specific performance requirements for the exhibit. It needed to clearly teach engineering concepts, represent 3 engineer degree programs, meet ADA accessibility expectation, and hold visitors' attention for about 8 to 10 minutes. We also designed it to stay durable for around 2 to 3 years and remain within our $150 budget. More technical requirements included using an Arduino, a motorized base plate, 3D printed components, and a tray of plastic blocks. These features ensure the exhibit is safe, functional, and educational. What makes our design unique is its fully hands-on experience. With an Arduino-powered shake plate and custom 3D printed blocks, students can build structures, test them, analyze results, and redesign, mirroring the real engineering process. This directly ties into the theme of improving urban infrastructure by showing how engineering decisions shape a city's ability to withstand earthquakes. To solve our problem, our team analyzed how to make the exhibit interactive while also keeping it budget-friendly, accessible, and educational. We designed the shake plate to simulate earthquakes realistically and in ways kids can safely experiment with. By blending engineering concepts with exploration and creativity, our project encourages young visitors to think like engineers and understand the importance of resilient infrastructures in the real world.
During the build process, some on-the-fly alterations had to be made to the grooves where the rotating piece would fit. Originally, the groove was too tight and needed to be sanded down. Additionally, quite a bit of the prototype was 3D printed. This includes the frame, blocks, motor housing, as well as the rotating piece. The prototype performed as intended. The 2 motors spun in unison to spin the rotating piece, thus shaking the plate. Originally, it was thought that the shake plate could be independent, with a motor under the plate to give off the shaking motion. This concept was seen as too complex given the time frame we had. So instead of a plate that shook individually, we thought of a rotating piece connected to 2 motors that could provide a shaking motion to whatever would be placed on the plate. Moreover, during the first test, we realized that the motors needed a housing that would keep both of them level.
In terms of cost, we were fortunate enough to reuse parts from previous projects and materials from the 1300 store. With those resources, our expenses were minimal. However, if someone were to recreate the prototype without those materials, the final cost would be around $34.69. Working on this project taught us a lot about flexibility and iteration. We initially struggled because the motors were shaking the frame instead of the plate itself. And after experimenting with placement and impact points, we discovered that the plate needed to be struck by the spinning lobe to generate the strong motion we wanted. This trial and error process helped us understand how small adjustments can dramatically affect performance. Overall, we would consider the project a success. The machine consistently shakes as designed, and we've learned valuable lessons about adaptation and problem solving. Our next steps are to present the project video and continue refining our understanding on how to communicate engineering concepts through hands-on demonstration.